about specters and exorcisms. Very exciting. Go ahead.
Okay, thanks for the introduction. So today I'm going to talk about some ongoing work with Marco Patrignani, which is sitting there. And it's going to be about Spectre and secure compilers. So let's start with Spectre. I guess most of you know something about Spectre. Spectre is a very recent new class of attacks, which has been discovered by people down here. And there are two important points about Spectre. The first one is that it exploits what is called speculative execution, and I'm going to explain it in a second. And the second important point is that almost all modern CPUs are affected by Spectre-style attacks. Okay? And well, since the discovery of Spectre, researchers tried to come up with countermeasures, and a particularly interesting class of countermeasures for the risk is compiler-level countermeasures. So, for instance, what happens here is that the compiler slightly modifies the program and inserts instructions here and there. For instance, you could insert fences to selectively stop speculative execution, and you actually have countermeasures in quite a few major compilers. Microsoft, Intel, ICC, and Clang all contain some sort of countermeasures. The problem is that, well, current compiler countermeasures are developed in an unprincipled way, and they kind of don't really provide guarantees. Okay, so what we are trying to work on is, what we want to do is we want to formally reason about the security of compiler-level countermeasures, leveraging some concepts from secure compilation. So it's work in progress, so I don't really have many results to show. I probably have more questions than answers, but I hope the rest of it is going to be interesting. So let's start with speculative execution 101. And let's start with a specific case of speculative execution, namely speculative execution over branch instructions. Let's consider this very simple program. So, okay, one note first. CPUs speculate over more than just branch instructions. There is a ton of speculation going on. For simplicity, for our talk, we're just going to focus on branch instructions. Okay? Okay, so consider this very simple program. We check whether the value x is under some bound. In this case, it's in bound of the array A, and if that's the case, we use x to look up into A, and the result to look up into B, and we assign it to 1. Okay? Very simple program. So when the CPU is executing this program, we start with the branch instruction, and for checking the branch instruction, we have to evaluate whether x is in bound or not. Doing this comparison, however, takes some time. For instance, size might have to be fetched from the main memory. And what the CPU does is that rather than waiting, the CPU simply guesses what the outcome of this condition is going to be and continues the execution based on this guess. Okay? So a bit more in detail, what the CPU does is the CPU queries a component called the branch predictor, and the branch predictor does some magic and will tell us whether the condition is likely going to be satisfied or not. Okay? Few more details. Branch predictor is actually a number of counters implemented in the CPU, and the prediction depends on the branch history and on the structure of the program. Okay? So let's say that the branch predictor tells us that the condition is satisfied. We continue the execution based on the guess. We perform the memory accesses. We do this regardless of whether x is effectively in bound or not. And at the later point in time, the CPU will be able to check whether the prediction was correct or not. If the prediction is correct, great. We saved time, we executed instruction in advance. If the prediction was wrong, well, it's not really a big deal. What the CPU does is simply discards the changes and restart the computation. Okay? So everything sounds kind of perfect. There is one tiny little detail that is very problematic from a security perspective. Namely, what happens when we discard the changes? So what current CPUs do is they discard changes to the so-called architectural state. So for instance, content of the register and content of the memory is restored. What CPUs don't modify is the microarchitectural state. This, for instance, contains caches. So we have some garbage left in the microarchitectural state, and this is what Spectre attacks exploit. So let me give you one slide overview of Spectre, and in particular we're going to focus on a specific variant called Spectre V1, which exploits two things branch prediction and caches. Here we have a happy cache, which for all our purposes is just a small memory stored recently that stores recently accessed data. And well, the setting is the following: we have an honest process that runs the function containing the vulnerable snippet. We have an honest Spectre attacker here. We need some information, like let's say the size of A is 16, and the goal of the attacker is learning what is in A of 128 in the honest process memory. Okay? So this is not part of the array A, it's just out of bounds somewhere in the honest process memory. And the only thing, there are two things that the attacker can do. They share processor, so they can execute, they can both run, execute things. And the other important point is that the Spectre attacker can trick the honest process into executing F with attacker provided values. Okay? So the attack works in 4 phases. We start with the training. So if you remember what I said before, the prediction depends on what has happened in the past. So what the attacker can do is just tricking the honest process into executing F with values of X which are in bound, for instance F0, F1, F2, and so on. Oops. At the end of the training, the attacker is sure that the next time the branch predictor will be called, this condition is going to be predicted as satisfied. Okay? Second step is some preparation. The attacker just primes the cache. Actually, it fills the cache with attacker controlled data. Third step is where the actual attack happens. The Spectre attacker tricks the honest process into executing F with 128. When the CPU executes, the branch instruction, it will appear the branch predictor, which we trained beforehand, so it will be treated as satisfied. We continue with the execution, we perform the memory accesses. Okay? So what happens now is that these memory accesses leave a footprint in the cache. And in particular, the second memory access will load a block from the array B somewhere in the cache. Okay? Later, the CPU realizes that the prediction was wrong. We terminate the speculative execution, and we go down the right path. But still, there are 2 important points. The first one is that, well, the gray thing here persists, so it's going to survive the termination of speculative execution. And the second important point is that the position in which the gray block here is loaded in the cache, depends on A of 120, on the value of A of 128. Okay? And last step of the attack is the extraction. The attacker can just recover the value of A of 128 by probing the cache and understanding in which of the lines the gray block is being positioned. Okay? So that's Spectre in a single slide. Why it is relevant, why it's problematic? Well, the Spectre attacker can just access arbitrary memory in the arbitrary locations in the honest process memory by simply exploiting these speculative execution side effects. Okay? So, as I said before, we have compiler level countermeasures, and in particular, there are two main countermeasures adopted by current compilers for Spectre V1. The first one is the injection of speculation barriers. So, in x86, the lfence command acts as a speculation barrier, so speculative execution doesn't proceed after lfences. And what compilers do, some of the compilers inject lfences pretty aggressively after each branch instruction. For instance, you would have something like the vulnerable program would be rewritten something like this, right? And here the fence stops speculative execution. And well, if you put fences everywhere, it kind of works. And the second countermeasure is slightly smarter. It's called speculative load-hardening. And the idea here is that rather than stopping speculative execution, you just want to make sure that nothing sensitive leaks. Okay? So how this is done? Well, you inject some data dependencies and masking operations, and the goal is stopping speculative leaks without effectively stopping speculative execution. Okay? I'm not going to go too much into details, but here I modeled this with this mask. It's not really faithful. in practice, something like this happens. You would set a flag, you conditionally update the flag based on whether you're mis-speculating, and then you use the flag to mask everything that could flow into the cache. Right? For instance, here we mask the value, the A of X value that we're going to use to look up into B. Okay? Key point, why does this work? Well, current architectures don't speculate over conditional loops, but speculate over branch instructions. Okay? So that's kind of most of the background. So before looking into, well, how can we reason about countermeasures, we need to figure out how to model and how to formalize the effects of speculative execution. And the next slide, sorry, the next slide is based on some recent work that we did, which is going to appear at Oakland, but somehow Dan did something, Marco also at another framework. So there are a few kind of similar frameworks with advantages and disadvantages. But how does our framework look like? We have three components. We have two semantics, which model the program behavior with and without speculative execution, and we have an attacker model which captures what the attacker can observe. And let me quickly go over three components. So the first is the non-speculative semantics. Non-speculative semantics is a standard imperative style semantics for a small assembly style language. So there is nothing really fancy going on here. Speculative semantics is more interesting. It captures the effects of speculatively executed instructions. I'm not really going to go into the details, but what we do is we extend the standard semantics with a concept called the prediction oracle. The prediction oracle abstracts away all the details of branch prediction strategies, and concretely what the semantics does is that whenever we execute the branch instruction, we start what we call a speculative transaction, and we query the prediction oracle for knowing where to go and for how long to speculate. And then we go down, we execute the speculative transaction. At the end of the speculative transaction, we check whether the prediction was correct or not. And in one case we commit, in the other case we discard the changes. Okay, and we restart from the correct branch. And the last thing that we need is the attacker model. So we consider an attacker that observes the execution of programs and sees three things: location of memory accesses, targets of branch and jump instructions, and beginning and end of speculative execution. So this is a very simple variant of the standard constant time observer, and the main advantage is that this allows us to, for instance, not having to model caches and other microarchitectural components explicitly. Okay, so before moving on to, well, what does it mean to be secure against Spectre attacks, I need to use some notation and give you a few information about our semantics. Okay, so given a program P and the state S, I'm gonna write P non-spec of S to determine the trace of observations that our attacker can see when executing the program, starting from the state S under the non-speculative semantics. And I'm going to use P-spec of S for trace associated with the speculative semantics. Okay? So there are two important informations about our semantics. The first one is that the semantics tracks the speculative context for register and memory. So for all the information that we stored in the register and the memory, we know under which speculative transactions they've been accessed and whether the transaction has been committed or not. And the second bit is that the semantics allows us to distinguish whether observations are happening inside the transaction or not. Okay? So concretely, the green observations here happen in transactions that are going to be committed. Observations in the red part are those that belong to transactions that are going to be rolled back. Okay? And for this reason, we can actually prove a very simple lemma, which allows us to always recover the corresponding non-speculative trace from each speculative trace by simply squashing the red part. Okay? And this projection is what I use this blue NS. Okay? So that's more or less kind of everything. And the interesting part of the talk is security conditions. Now we have a vocabulary for talking about whether programs are secure against Spectre attacks. And what I'm gonna quickly go over is 3 criteria of security, which kind of span a bit different ideas of security, and somehow criteria on this side are very, let's say, are very difficult to check. Criteria on this side are easier to enforce. But somehow we have strict speculative safety, and speculative non-interference. And I will start with strict speculative safety. So strict speculative safety is a very conservative security condition against Spectre attacks. And informally, we can say that the program is strictly speculative safe if there are no observations in the speculative trace. Okay, there are no speculative observations. So no observations that happen inside transactions that are wrote back. Okay. So what does it mean? Concretely, we can just formalize it by requiring that the non-speculative trace and the speculative trace are the same. Okay, so this is very simple. It does intuitively make sense from a security perspective, but somehow it doesn't really simply tell you that, well, there is no speculative execution. Okay? So we can try to do something better, and you can actually formalize this. We formalize this doing something better with this notion of speculative safety. Sorry. You can actually just rewrite, using the trick of the projection, you can just rewrite everything in terms of the speculative semantics. So you just want the non-speculative projection to be the same as the entire trace. So you can do something better. You can allow some sort of speculation. And how can you do this? Well, you can move to speculative safety, which is a more permissive variant of strict speculative safety. And informally, what we allow is we allow speculations that we allow speculative observations that refer only to non-speculatively accessed data. Okay? So concretely, we're just saying that you can do speculative execution as long as you just do it in a safe way. Okay? And how do we do it? Again, we kind of do some tricks and relax a bit our notion of projection. And again, you have a property of the same shape. You just require that the trace under the speculative semantics is the same as the safe projection under the speculative semantics. Okay? So last bit, and this simply drops unsafe observations, those that would depend on speculatively accessed data. And the last security condition is speculative non-interference. So this is what we presented in our Oakland paper. So speculative non-interference is the most general security criterion, and it is inspired by non-interference. So at a very high level, we say that program P is speculatively non-interferent if the leakage of the program under the non-speculative semantics is the same as the leakage of the program under the speculative semantics. Okay? Concretely, you can formalize it as follows. You just require that for any two program states as S prime, whenever the non-speculative traces are the same, then the speculative traces are the same as well. Okay? So what this security condition gives you is that no matter how you do speculative execution, you're not going to acquire more information from speculative execution than from executing the program without speculation. Okay? And again, you can simply do the trick and rewrite it as and write in a way that refers only to speculative semantics. So back to square one, and now we have the three conditions, and there are a few important points that I wanted to make. The first one is that, well, you can state all the condition only in terms of the speculative semantics. Second important point is that strict speculative safety and speculative safety are effectively safety properties on the speculative semantics. Speculative non-interference is a two-way per safety. You actually have implication in this direction. So these are simply sufficient condition for speculative non-interference. And let me now connect it to, well, countermeasures. Why we came up with these two conditions is, well, our current conjecture, we haven't proved it yet, is that naive compiler that does fence insertion actually enforces speculative safety, strict speculative safety. Naive compiler that does speculative load hardening enforces speculative safety. Okay? So somehow the difference between these two countermeasures lies in this smarter way of doing projections. Okay? So, super quick conclusion, secure compilation for Spectre, work in progress, so it's a roadmap. We don't have actual results. But the setting that we plan to focus on is the following. We're going to consider a simple assembly style language for source and target. Key difference between source and target is in the semantics. In the source language, we just consider the non-speculative semantics. In the target language, we are going to consider the speculative semantics where we can do speculative execution. And the key point here is that all the security conditions are trivially satisfied in the source language. So secure compilers will effectively enforce the security condition just in the target language. And the main question is, well, which security criterion should we get? So we can turn to the fancy diagram from Carmine. And I think following our insights on the properties enforced by countermeasures, we have two main ideas. The first thing is we could try to do some variant of robust safety property preservation, since current countermeasures effectively enforce the safety properties. And the second idea is robust two-way per safety preservation, since, well, speculative non-interference is two-way per safety, so a variant of this could probably work. And yeah, I think I have fancy things, but I would rather not go over it and conclude here and take questions.
So we have time for a few questions. Yes. Yeah.
Should I like or anything or no?
Ah, okay.
Should she use the mic?
Should I use the mic?
No.
Okay, okay, great. Right, so I think it sounds like you're sort of proposing that these two mitigations that are commonly used in software correspond to these two different security conditions. Does that lead you to potentially another mitigation that corresponds to the speculative non-interference?
It's a good question. We don't have, at least I don't have yet a good idea for, I mean, you could try to do something smarter than just considering the safety behavior, you know. I mean, I think if you do, let's say, a smarter way of placing things could probably allow you to move towards the IP property.
Yes.
You define your leakage in a certain way, like leaking the addresses, I think, that were accessed.
Yeah?
Is there any way to be sure that that is sufficient?
No. But I mean, sorry for the direct answer. But, I mean, in practice, no. Concretely, what we did is trying to be very conservative in the sense that using this attacker model where the attacker can observe like memory accesses and program counters, kind of reduces a lot the assumptions on the microarchitectural model. So somehow, for instance, I don't know, if you give away the addresses, you know, somehow you just ignore caches, right? Somehow, and same program counter. And, but I mean, in principle, no. There is a huge issue of model validation.
So we have a bit of tight schedule, so I would say let's move on.
Yeah,
Other
I guess
questions
we
later
can
on.
do
Yes.
So
Now we switch. Yes.
Yeah,